welcome to the Robotics Symposium. So today we have Todorov, our own professor. Emmo is the type of person who is so passionate about their research that rather than inviting somebody, they said, "Oh, I'm going to give a talk myself." But he has been working on MuJoCo for a while. He's also the kind of person who touches every line of code of the research product. And it's going to be some of the very recent results related to MuJoCo.
Yeah.
So
thank you so much. Thank you everyone for coming here. Robotics is a wonderful idea. It's really popular. Here's the original idea. So the idea was that humans, everyone is going to be a boss. You sit in the comfort of your armchair. You have a team of slaves named the robots. They're like servants. You tell them what to do, and they go do it, and you go play golf or whatever it is that you like to do. And it caught on because that's what every human wants to do, right? About a century later, we have exactly the opposite. We have a team of humans working for a robot that's trying to kill itself. Of course, we have scientists for robots like assembling laptops and such, but the kind of more interesting robots that we're trying to build is really we're not there. And the reason we're not there is because automation is just lacking. I mean, whenever something works, it works because it was tweaked and hacked and fine-tuned and videotaped once for the YouTube demo, and then somebody moved on. So it really needs automation. And I think the key to automation is to do high-performance numerical optimization and take advantage of modern processors. And so this talk is about how to do that. In particular, I like model-based optimization, and I want to explain to you why. So here's the general idea. First, we design a physics-based model, meaning a model that reflects our knowledge of physics. That's one of the few things that we actually understand, so we might as well use it. These models obviously have parameters, so we have to fit those parameters to experimental data. It's usually called system identification. You can call it learning if it sounds more modern and exciting, but it's really the same thing. Usually you need to design a state estimator, which of course uses knowledge of the model and does some approximation to Bayesian inference with respect to the model and clean up the data and tell you where you are. You need to design a feedback controller. This is mostly what I'm going to talk about today, but the general idea would be that if you have a model and you have some performance criterion, you can consider lots of different feedback controllers and pick the one that seems to work well. Then you have a closed loop system. You want to make sure, at least in simulation, that seems to be robust to simulated sensor noise and model errors that are unavoidable. And if it seems sensible, you go test on the real system. And then you're going to collect data, and then things are going to go wrong, and you have to adapt it somehow. Now, one comment I want to make here is that when you work with real machines, you have a lot less data than, let's say, when you do computer vision and you collect images from the internet. And there are multiple reasons for that. One is that perception exists independent. I mean, the data for perception exists independent of the entity that does the perception, right? The world is out there. You need a camera. You don't need a brain or a computer to process the data. Data that comes from control only exists after the control system is there. And so before you have a control system, you don't have data. You have things just dropping on the floor. That's kind of boring. Also, things just break, and graduate students complain if you ask them to collect too much data, and they switch advisors and go to work with somebody in computer vision who already has the data. So we don't push our graduate students too much. So the reason I call this adapt is that I believe you really need to do a lot of work in simulation, and whatever priors you can get from prior knowledge, you want to embed those, and then you only want to make fine adjustments given the real data, as opposed to trying to learn brute force from it. And this is obviously in contrast with things that are popular today, such as neural networks used for reinforcement learning. What these methods do is, if you look at all the papers out there, they require vast amounts of data. And this data is not available, and it's not going to be available. So basically, they're model-based, just like what I'm going to be talking about is model-based. They're model-based in the sense that the only way to run them is to have a simulation model. And the funny thing is that they pretend not to be model-based for the purposes of looking good in academic settings and writing papers. But really, they're as model-based as anything else. And they're just missing on the advantages of explicit model-based approaches. So as far as I'm concerned, that doesn't make much sense. But this is certainly a different way to use ideas of optimal control to design controllers. You can use a neural network or something like reinforcement learning and do brute force data collection and fit it. So in that sense, it's not that different from what I'm going to talk about. Yes?
Could there still be an advantage to the learning-based techniques in saying, I'm not trying to advocate that everything should be learned, just as a caveat, but could there be a benefit to saying that the learning-based techniques might be easier to tweak on the real data because they already showed that they can be tweaked towards the simulator?
Well, the problem with tweaking for real data is that if you have too many parameters and you have little data, you're going to overfit badly. The only thing that would ever save you from overfitting is having the right priors, right? And what physics-based modeling means is that you use the right priors. Now, if you could take something like a neural network and constrain it to only model systems that are physically plausible, or to only model controllers that are near optimal for some sensible system, that would be great, but no one has ever done that. Right? Basically, what that means is training not only one network, but somehow discovering the entire submanifold of networks that correspond to sensible things, and then when you get data, just move only within that manifold. If you don't do that, and if you just allow everything to be unconstrained, you're going to overfit, unless you have vast amounts of data. So I think flexibility comes at a price, right? There's a danger of overfitting.
And another
go ahead.
You could still argue that even though the learning techniques just are based kind of to copy kind of the controller, but they can still then have the benefit of being vastly more efficient later, right, once they are trained, than running through the model-based approach all the time.
So model-based approach, that doesn't necessarily mean that you're going to do MPC, although I think it's a good idea. But you could cache the results of model-based optimization into something that mimics the controller to some extent, which is in line with what I'm saying. You do a lot of work in simulation, get something that works, put it on the real system, and then use wisely the small amounts of data that you get. And what exactly you do with that data, there are lots of things you could do with it. I mean, another thing you could do is use data to learn a simulation model and then do model-based optimization with respect to it. So my focus is on control design. So I'm going to be talking mostly about this part here, about designing feedback controllers. And I'm interested in sort of dynamic environments where robots interact with the environment through contact dynamics, and things get really messy and complicated, but also exciting. The tool that has proven to work better than anything else is trajectory optimization. What does that mean? It means that trajectory is a sequence of states or a sequence of controls that gave rise to those states, the kind of equivalent. You think of the whole trajectory as one object, and you ask, in the space of all possible trajectories, which one do I pick that's going to do the job for me? You could do that either in real time or offline. The real-time version of trajectory optimization is called model predictive control, or MPC. The idea is really simple. You start somewhere. You have some running costs that you add up to some time horizon. You may evaluate some kind of heuristic approximation to the cost-to-go function at the horizon, if you have one. If not, just don't. OK, you plan up to some horizon. You start executing. What actually happens may deviate a little bit. You sense it. You plan again. And so there's this bundle of trajectories that kind of pulls you forward. And people have been doing that for a long time for things like controlling chemical plants, for example, because these things are sufficiently slow and smooth that the existing optimizers can outrun the real-time clock. For robotics, this used to be done for reduced models. When we started doing this work about 6 years ago, we realized that the tools are now there to do it through the full dynamics without their glorious complexity and actually work. So you've probably seen some of those movies. I'll go through them very quickly. So here is there's the optimal control problem. Cost function says put your body over the feet and don't move too much. So basically stand. And what we're doing is we're delivering like huge perturbations to this thing, and the MPC in real time is figuring out, how do I save myself and recover. So all of these are fully automatically discovered things on the fly, no prior learning. Like this thing knows physics, it knows how to do numerical optimization, and it knows what the cost function is. That's it. Here's another example. Here the cost function is basically not to fall. You can actually tweak the parameter. So if you have multiple terms to this cost function, you can change the weights in real time, and you can switch between behavioral regimes. So here, for example, we told it that we don't want it to drive around. So now it's forced to start using its arms to balance, and it does that. This is something that Vikash did here. The cost function says that the object has to go somewhere. and please figure out what to do with your hand to make that happen. And so everything that the hand does is just a byproduct of optimization. Here's something heroic that Svet continues to work on. This is actually tricky, but basically here the cost is to put the object somewhere, and the robots have to do whatever it takes to keep it there. So you can do all kinds of nasty perturbations that you're not supposed to do. So MPC is one approach. Obviously, it's very computationally expensive, right? You're doing this in real time. So in practice, you can plan on the order of 1 second into the future, maybe a couple of seconds if you make some assumptions, but not much more than that. So how could you ever do anything sensible by planning only a couple of seconds? Well, the interesting thing is that when you're controlling these complex dynamical systems, if you don't crash for 2 seconds, that already means you're really, really good, because almost everything is just going to crash instantly. And so another way to put it is that if you contrast this with games like chess or Go that was recently done, or other things, when you're playing games, there is a reward or a penalty only at the end of the game, right? So you play for a long time, nothing happens, and then you win or you lose. So in that case, you really have to do either long-term planning until the end, or you have to approximate some kind of cost-to-go function heuristically with neural network or handcrafted approximator or whatever. When you're doing control, like let's say you're walking, a sensible cost function says that keep moving forward and don't fall below some elevation, because that means you're falling, and keep energy small. Well, so if you optimize that cost function over a couple of seconds, basically maybe over 2 steps of a walking cycle, you basically know how to walk. So it's a very interesting thing. The spatial complexity is much higher, and the dynamical system is, well, it's continuous and prone to instabilities and all kinds of nasty positive feedback loops. But on the other hand, the temporal planning problem is not nearly as hard, because there is the very simple cost functions contain a lot of information of what it means to perform well on relatively short term. So there's really a trade-off between like spatial complexity and the temporal complexity of planning, which is why these MPC things can actually work, even though they have shockingly short planning horizons. Of course, you could do longer-term planning horizon. With, this is an example of something that Igor Mordak did called contact invariant optimization. So this thing can plan sequences of like 10, 15 seconds. The one thing we did here is plan a bunch of trajectories and then use a neural network to cache the solutions, basically. And this is done in a coupled way, where like you train the network a little bit, then you use that to warm start the trajectory optimizers. They optimize a little bit, take that data, retrain the network, and keep the 2 of them in sync. Closely related to the guided policy search that Sergey Levin has been doing. So this turned out to work quite well. So here, this is an example of what Dieter was mentioning earlier, that if you do this real-time optimization, obviously you need a lot of computing power. But if you do it offline and then you cache it into some neural network, then executing that neural network online is much faster. So here the network is trained to control this bird. There is a target. The inputs to the network are the state of the system and the target. And the network figures out how to make the system follow the target by stepping, in this case. So yeah, you can just control this guy in real time, and he steps around. The physics here are not entirely realistic, and actually in this talk I'm going to resolve that problem, but I mean, you can see that it works quite well. You can change the body morphology, you can have multiple feet if you wish. This is how your sofa would normally walk. Here's a donkey of some sort. Make it those sideways things. Here's a spider. So this is another possibility. Train lots of pieces of trajectories into a model and cache them into a neural network. Again, model-based thing, because you need the trajectory optimizer in the model. Now, would this carry over to real hardware, given that there's probably going to be model errors? And there's something called robust control that attempts to ask that question, and unfortunately it doesn't know how to answer it, unless the system happens to be linear, and systems are not linear. So there are some tools that people are trying to build that are just not ready to scale. And in the meantime, the answer is empirical. It either works or it doesn't work, so you have to try it. So I'll quickly go through a list of examples where this thing works really well. And you've probably seen most of them, but just to remind you. This is Peter Abill's work, which is what made him famous. So So here what he did, he basically built a model of helicopter dynamics and then used model predictive control around. So he recorded trajectories from human radio pilots and kind of averaged them, and that became the cost function. And then he used MPC to track that cost. And he made these helicopters do amazing, like, aggressive maneuvers. Is this the physics model perfect? No, and the sensing isn't perfect either, but the imperfection is small enough to not crash into those trees over there. Here's something that we did. Here, this is a model, this is a little robot that's in the lab. The cost function says hit the ball in such a way that it comes back, basically. And you can go and like perturb it, and it's perfectly reactive. You can drop another ball at some point, and it bounces two of them. So here again, the model is not perfect either. In fact, Paul used an embarrassing hack at some point. The restitution was such that the model was predicting that the ball would fly higher than it actually did. And he said, OK, fine, I'm just going to change the cost function to ask it to fly higher, and then it will fly to wherever I want it. So you can, I mean, there are things you can do. But again, it's a very jittery dynamical system, imperfect model. The thing works. Here's something that my former postdoc, Evangelos Todorov, did recently in his new lab in Georgia Tech. So this is, here they have a model of this car. They have a GPU in the car. It's doing model predictive control in real time, planning through the physics of the car as they modeled it. And this thing is happily driving around quite aggressively. They have more, I can drive in different directions. And you can watch it online if you want. It's pretty cool. This is actually an example where, so Evangelos was telling me that now they've been able to collect data from this thing and replace their physics-based model with a neural network and then plan through it, and it works maybe even slightly better. But it's an example where, one, the system is sufficiently low-dimensional, so you actually can hope that the data covers the entire space. And two, they have a really good baseline controller that already puts them in the regime where they can actually collect data. And three, the car is not going to fall because it's already fallen in some sense, right? All its wheels are on the floor. So, but nevertheless, that's an example where you can actually do model learning from data. This is another example where that we did. So this is probably the hardest thing that has been done up to now because it's a high-dimensional and really complicated system. So here what we did is that if you just take the model, optimize the trajectory through it, and run it on the system, that fails. So what we did instead is, in simulation, encourage the optimizer to find robust solutions. And the way we did that is we said, here are 10 different models of that robot that differ with their mass or such things. I want one trajectory that's going to work for all 10 of them in simulation. And the idea is that if I find such a trajectory and then the real model, the real robot is somewhere in between those 10 models, then it will probably work as well. And you just saw that. So I think this kind of ensemble optimization is very promising for achieving robustness. I mean, you might kind of take a Bayesian view and say, well, let's just take a probability density over models and optimize some kind of expected or maybe worst case performance. Trouble is that when you're in these high-dimensional continuous spaces, the moment you start talking about probability distributions, in the very next step, you're forced to adopt a point estimate or just the mode or the mean, and you end up with linear quadratic approximations. And the trouble with those is that for a linear quadratic Gaussian system, the noise does not matter, and the uncertainty does not matter, and the optimal controller for the reference system is the same as for the distribution. So sampling seems to be a good way to get around that, and the number of samples is surprisingly small. So what I showed you here is that we only use 10 samples in model space, even though it's high-dimensional space. But that was enough to give us robustness. And let me just show you one last example. Yeah, go ahead.
So when you sample, do you just sample the initial kind of properties of the robot, or do you change it also over time?
No, we don't change it over time. If you don't want to change it over time. See, if we allow the thing to do system identification adaptively online, it would kind of lock onto one model, and it will assume that this is the model, and it will become very aggressive with respect to it. And then if there's model error, it's going to fail. So it's very important to prevent adaptation, actually. Yes?
So your initial model comes from system identification, and then you just randomly...
It's kind of manual heuristic yeah, look at the robot.
You put together plausible physical.
Yeah, so I mean, so this thing has 20 actuators that are identical. So Kendo did a very careful system idea of the single actuator by taking it apart or whatever. But then once you put all 20 of them in the robot, I don't think we've done it as carefully as we could. You would think that actually, if you do system ID in a Bayesian sense and you have an uncertainty over model parameters, you could actually sample from that. But it's not clear that's the right thing to do because you don't necessarily want to represent the model errors. Instead, you want to represent the model errors that are likely to hurt control performance. And not all model errors do that. And there's nothing in the system ID that tells you which. So it's possible that human intuition is more useful in this sense than actually doing the math.
And then when you generate the other models, is that a random perturbation or?
No, they handcrafted them. But they just picked the things that seemed like they're going to be important.
It shouldn't hurt to represent all of those errors, though, if it's not going to hurt the control performance anyways.
It will hurt it in the sense that if you have 1,000 models now, you've made the problem a lot harder. But other than that, yeah, you're right. I mean, the bigger you make the ensemble, the better it's going to be. It's just that it's a trade-off. Actually, so this is obviously done offline. I mean, I'm hoping to get to a point where we can actually do this ensemble optimization in real time in MPC mode. And I think using GPUs, we can actually get there. Last thing I'm going to show you on the real robot is this thing that we did with Vikash and in collaboration with Sergey. So this is again trajectory optimization. The cost function says spin this object somehow. Now the trajectory optimization is done with respect to a locally linear model that is learned from data. So there's no physics-based model here. So we started with some situation that's kind of passive. Initially, it doesn't do anything. We plan a trajectory, we execute it, it wiggles a little bit, we collect data. We basically fit time-varying linear regression to that data to build a very naive linear mapping from sensory inputs to whatever next states. And then we say, OK, now this is the model, do trajectory optimization through that, improve a little bit, and iterate. Of course, it's only local, right? You're only learning around that state, but if you're willing to live with local, then it looks like you can do it. What Vikash and Abhishek at Berkeley have been trying to do more recently is to build multiple models and multiple executions that work with different configurations and then try to interpolate them with a neural network. It seems to somewhat work until Vikash's hard disk crashed and he had to reset the project. But hopefully, on the second pass, it's going to be even better. So there are plenty of examples where you take these really interesting dynamical systems and you do these really aggressive behaviors and things actually happen. And there's certainly more to be done in terms of transferring model-based control to real systems and dealing with robustness and making them adaptive. But that's not what I want to talk to you today about. The reason I said that is to reassure you that investing in model-based optimization is worth it. Now, the rest of the talk, what I'm going to tell you about is how to make model-based optimization better. And fair warning, this actually has math. So I apologize in advance. OK, so we're going to start with hand-waving intuition. So I already mentioned this earlier. It looks like the spatial complexity it looks like staggering and hard, but it can be resolved on a relatively short horizon. And that frees you up to do temporal planning that's not actually that hard. So I'm going to actually take this to an extreme, and I'm going to do the following. This is my robot. Imagine that I take an optimizer and put it into the robot, like just to make it physically sort of anchored. Suppose there's a computer inside the robot that's going to run an optimizer. And I'm going to draw a box around this whole thing, and I'm going to make that the robot. So I define the robot and the computer in it to be the robot. And now the robot has a state or state estimator. It goes to the optimizer. The optimizer gets a cost function instantaneously, optimizes it, and figures out what the control should be, and then applies to the robot, and something happens. So to give you an example, suppose you have a dog, and you train your dog to, I don't know, sit and fetch when you tell it things. Now, when you command your dog to sit, you don't tell it how to activate all its muscles that make it sit, right? That would be like controlling the robot. Instead, you just tell it sit. You give it a high-level command, and there is something inside the brain of the dog that translates that into a very large number of massive activations that somehow make it sit. Right? So that's what I want. I want the robot to be like a little dog that can be controlled on a high level. Somebody still would have to do the high-level control, which could be a human operator in the setting of tele-operation or some automatic controller. But now that automatic controller is going to be generating high-level costs that are presumably easier to optimize. Okay? So we want to think of cost functions as being the control signal. Obviously, the space of cost functions is infinite dimensional, so we can't do that directly, so we have to somehow parameterize them, and we'll see how that works. That's the idea. Now, whenever you write something as an optimization problem, that in itself is boring until you can show that you can actually solve that problem. Because if you can't solve it, then sure, everything is an optimization problem, but who cares? So the important thing here is that if we want to call this a dynamical system, we have to make sure that whatever problem we're trying to solve here, we can really solve it robustly in real time and maybe even faster in real time, so we can actually think of it as a dynamical system. I'll show you that. Now, if you look at robotics, there are actually many examples. In fact, probably the most popular control approaches in robotics fall in that general category, and this is a generalization of all of them. The simplest thing is called computed torque control. So what you do here is you have a fully actuated system with a fixed space, industrial robot arm. You give it a reference trajectory, which you can think of as specifying a cost, just like Peterbilt had a reference trajectory for flying the helicopter. And then at each point in time, you can look at the position and velocity of the arm, look at the desired acceleration, do inverse dynamics, figure out what the control torques should be, send them to the robot, and it moves roughly the way you said, and then you can do a little bit of PD control on top of it to correct. Okay? So that disturbingly dumb idea accounts for probably 90% of the controls that have been deployed out there in the real world on actual machinery, because it's fully understood and it's limited, but it actually works. Operational space control is something that Khatib pioneered, and there have been many people who went through his lab and elsewhere who have been using it. So the idea here is that you focus on something that you call the end-effector, usually a hand in manipulation, and you describe the dynamics of the system and various objectives in that space. And then once you figure out what to do in that space, you project back into the full physics of the robot so you can figure out how to control it. Okay? And this usually comes down to linear algebra. There are various pseudo-inverses that we end up using. I'll show you one of these later. The latest hit is to use quadratic programming. So roboticists finally figured out that quadratic programming can be solved in real time, and they have been fascinated by it. There was a recent meeting where Chris Atkinson described that as an alien technology that was beamed to Earth and is changing the way we do things. I'm not kidding. That was a high-level NSF workshop for deciding the future of robotics funding. So what's going on here? So this has been very popular. So what you do here is you plan through some usually reduced order physics model, and then at each point in time, you solve a quadratic program in order to figure out how to control the robot. Probably the most salient example is in biped locomotion, so the DARPA Robotics Challenge. Most of the winning teams converge to that sort of strategy. So the idea is that you think of the robot as a slip-loaded inverted pendulum, it's a reduced model, plan some kind of center of mass trajectory, for this very simplified system. And then at each point in time, you say, OK, I have my robot. I want my center of mass to accelerate that way. How do I actuate the robot so it indeed accelerates that way? Okay? That's a quadratic program because you have to make sure that you don't slip and contact forces within the friction cones and such. But you can solve it very quickly and control the robot that way. The quadratic people have been using that extensively. So Vijay Kumar and Claire Tomlin and those guys use it all the time and make the quadrators fly. Looking at stabilizing an object in the hand just for achieving a passing grasp, that can also be written as a QP. So what I'm going to be doing here is a generalization of that. And the generalization is the following. So if you have a system that has constraints, either contacts or joint limits or friction, what happens is that the relationship between control and acceleration becomes non-smooth. So normally, if you think F equals ma, there's a linear relationship between control and acceleration. However, when you have contacts, here's a simple example. If I push that way, the acceleration is going to be 0 or almost 0 if it's soft. If I push that way, acceleration is going to be big. If I push that way, acceleration is going to be somewhere in the middle. right? And so these are really, really discontinuous regimes, right? Now, if I have 10 or 20 contacts that are active, I have 3 to the power of n possible dynamic modes. So we're talking about billions of possible dynamical systems that each of them is smooth, but the transitions between them are actually, they actually have sharp edges, okay? What the QP approach does is arbitrarily picks one of them by somehow deciding that, let's say I don't want to slip or whatever, and tries to solve for that and basically ignores everything else. As a result of that, it cannot really exploit the fact that contacts give you control authority and enable you to do things that you couldn't do before. So what we're going to do that is we're going to get rid of this restriction and end up solving a much harder problem. In particular, our optimizer here will end up solving a non-convex and non-smooth optimization problem. And nevertheless, it's going to do that in less than a millisecond. And we'll see how that works. Just a bit of notation. Q are going to be configurations. V are going to be velocities. You can loosely think of it as Q dot, although if you have quaternions, it's not exactly Q dot, but whatever. Tau is going to be an applied force, which has the same dimensionality as the velocities and number of degrees of freedom. So for a humanoid, think about 30 or 40 or something like that. Now, what makes control interesting is that you have under actuation. So when I'm walking around, I have 6 degrees of freedom that are not actuated, right? The translation and rotation of my torso. If you assume that my arm, my shoulder has a fixed base, but I'm manipulating an object, this thing again, it has 6 degrees of freedom that are not actuated. The others I can actuate, but these I cannot actuate directly. I can only do so through establishing contact, and that's what gives me control authority. Now, it's a shame because these unactuated degrees of freedom are usually precisely the degrees of freedom that we care about. And so if I manipulate an object, I only care what happens to the object. If I'm trying to locomote, I want to know where my body is. I don't really care what happened to my arms and legs relative to the body at any point in time. So it's going to be important. So we're going to take this applied force vector, and we're going to break it into 2 components. One is U is the control that we have access to, which basically the forces in our joint space. And Z are going to be these root forces, which would ideally be 0, like if we want the thing to be physically plausible. Okay? So we're going to partition them. And now we have dynamics. Think of it as continuous time. So for now, it's going to be some function of position, velocity, and control that tells you what the acceleration is. And then you can integrate that forward. You can make it discrete time if you want. Importantly, we're actually going to use the inverse dynamics. And you'll see later why that is. Inverse dynamics is a function that takes position, velocity, and acceleration and recovers the applied force. Now, the computed torque control that I mentioned earlier does exactly that. It does inverse dynamics, given the position, velocity, and desired acceleration. For a constrained system, however, it's not at all clear what the inverse dynamics should be, right? Because in the inverse dynamics implies that given the kinematics, you can recover the forces. But if I have a hard contact, if you look at me right now, you cannot tell if I'm just resting my arm there or I'm pushing against it. And there's nothing in the kinematic data that actually tells you what the forces are, right? So if we want to use inverse dynamics in a model-based approach, what we have to do is we basically have to make all the constraints slightly soft. So there is a little bit of acceleration whenever you push against anything, okay? And it's going to be very little so that qualitatively it doesn't actually affect the physics, but it's big enough for an optimizer to pick up a gradient and move in the right direction. Okay? So we're going to be using inverse dynamics, and we're going to, again, separate this into actuated and unactuated space. Now, here's how we're going to define the goal-directed dynamics. This is our dynamics, right? This position velocity control gives us the acceleration. The cost function that I mentioned earlier that we get to hand down to the system, that's our control input now. That's a function of acceleration. So we're going to be talking about cost functions in acceleration space. We're going to add to it some kind of regularizing cost, which is basically a norm of the control signals. The natural way to weight forces and controls is through the inverse inertia. I'm not going to go through the details why, but it has to do with differential geometry and such. And also actually works really well. So but you can think of it as technicality if you want. So we're going to be optimizing some kind of control or energy or regularizing cost, plus the cost that were handed down by the high-level controller. And we're going to be optimizing the over all possible controls that are admissible. And this admissible set is usually a box saying that stay within some bounds. Okay? So here's how we're defining the forward dynamics. We're saying the acceleration of this goal-directed system is the forward dynamics of the position, velocity, and the control, except we're not given the control. We have to find the control before we apply it. Okay? And so we have this embedded optimization problem inside our dynamics. Right? Now, alternatively, we can say the following. We'll say, let's work through inverse dynamics. So now we're going to define the acceleration of the system directly as an optimization problem over accelerations. We're going to constrain into a feasible acceleration set to be defined later. And now what we're going to do is now our cost function is just a function of acceleration, right? So the thing that used to be forward dynamics now just became a direct optimization variable. The thing that used to be the control became our inverse dynamics, because given the acceleration, the inverse dynamics can back out what the control was. Okay? And now what is this constraint set? The constraint set, the simple definition is this, like it's all acceleration vectors for which there exists a control such that the forward dynamics gives you that acceleration. Right? That's not a convenient definition. Turns out the inverse definition is better. So this is the set of all accelerations for which the inverse dynamics in control space puts us in the feasible box of controls, and the inverse dynamics in the unactuated space gives us 0. Okay? So you can see that basically what we have to do here is solve some kind of nonlinear inequality constraint on the inverse dynamics. And so that will end up being essential. And again, this control cost is, you could have picked it differently, but this just turns out to work well. Okay, so this is a definition. Like if we can solve either that or that optimization problem in real time, then we'll have our goal-directed dynamics. We can hand down whatever costs we want to it, and it's just going to do its magic, and our little dog is going to sit instead of twitching its muscle. Now let's just very briefly see how that works for operational space control. So consider a fixed base robot for now that doesn't have any constraints. M is the inertia matrix. This is the acceleration. This C stands for Coriolis, centrifugal, spring damper, gravitational forces. Basically, all the forces that are a function of position and velocity and do not depend on the control. Okay, and this is the applied force. Okay, so this is the standard robot dynamics. Now, suppose we want to control an end-effector. Okay, so JE is a Jacobian of that end-effector. Suppose we handed down some desired acceleration for the end-effector. This is the actual acceleration of the system projected in end-effector space. We're going to subtract them and penalize them, and that's a simple way to define these cost functions. Okay? Now, take this dynamics, this end-effector cost, and the optimization problem on the previous slide, and you can actually get an analytical solution. So here, the goal-directed dynamics are simply some kind of projection of this end-effector acceleration into the full space minus these bias forces, and then this is some kind of weighted pseudo-inverse. So like I said earlier, when you don't have constraints, it all comes down to linear algebra, and it's all very convenient. And if you weighted this differently, you could have gotten a different weighted pseudo-inverse. By the way, people who work in that field have spent decades figuring out which pseudo-inverse they should use, because when you apply them, you actually get different behaviors, and some of them are better than others. Anyway, so this is just a toy example to show you how you can handle this when you don't have constraints. Now, we're going to do this with constraints, and we're going to use the MuJoCo physics engine, which has this unique property that the inverse dynamics are well-defined because the constraints are soft. And so we'll be able to apply this framework directly. There's a book about it if you want to read. Briefly, in MuJoCo, the forward dynamics are also defined as an optimization problem, and that's the case with every other physics engine, like Bullet, ODE, Dart, whatever. The optimization problem is the following. So it's an extension of the Gauss principle of least constraints. So this says that F equals MA should be satisfied, and this says the constraints should not be violated, basically. Since MuJoCo uses soft constraints, this is a soft penalty function that depends on the acceleration projected in constraint space and then subtracted some bias from it. And interestingly, this is actually an unconstrained optimization problem, unlike every other formulation of contact dynamics where you actually have to solve something like an LCP, which is not only constrained, but it's NP-hard on top of that. This is just a convex, unconstrained optimization problem. Because it's convex and unconstrained, we can actually figure out the inverse dynamics analytically. Just take the gradient of that and set it to 0. And what we get is force equals mass acceleration plus these bias forces, Jacobian transports, and then this is the constraint force. So it turns out the constraint force is simply the gradient of this magic potential function that we use to penalize constraint violations. Okay? You can take one more derivative and get an analytical Jacobian of the dynamics, which is simply the inertia matrix plus JJ transpose, and this is the Hessian of our scalar cost. And again, this is something that we do analytically. So I'm going through this very quickly, but you have to realize this is very unique. Like there's no other physics simulator that actually has these analytical properties and computes them efficiently. And so this is the result of about 5 years of research into new types of contact dynamics that I'm not going to bother you with. I'm just going to illustrate to you what it looks like. So here, so you can see that you can make the constraints pretty hard. So here we're playing Jenga, basically. And these are soft constraints, and this has analytical and well-defined inverse dynamics, but you don't really see the softness. This is courtesy of Yuval Tassa, who is now at DeepMind. Instead of training neural networks, he's playing Jenga. Here is a VR application. So here, this is a stereoscopic system. You can go and interact with things and solve cute little manipulation problems, even though you don't have tactile feedback, interestingly. There's a learning curve here, by the way. When I first did this, I wasn't very good, and maybe after a couple of days of debugging the VR, I was surprisingly good at it all of a sudden.
So these surface constraints, how far away from the surface are they active?
You get to decide that as a parameter. The constraint is more like if you're penetrating into it, how much does it want to push back. But this is not, so importantly, this is not a spring damper. This just shows you different contact parameter regimes where you have different softness. Let me just answer this question. This penalty is a function of acceleration. When you think of a spring damper, it's a function of position and velocity. If you do that, the whole system goes unstable, and I mean that was basically abandoned. The people used to do spring damper models of contact, but it's not a good idea. This is something like a spring damper in acceleration space, which makes it a lot more stable and allows you to take large steps. So basically, this is a function over the difference between what acceleration you're experiencing and what you should be experiencing, given some constraint stabilization model that tells you what it would like to see, basically. So it says, OK, if you penetrate, I want you to be accelerating out that way. And now you take that as a reference and say, OK, I want my acceleration to be close to that, and I'm going to penalize that, basically. Yes?
So like in some haptics systems, when you touch the object, you get this kind of oscillation. Is that due to the fact you just mentioned, where they're modeling the interaction is just a linear spring instead of?
There are multiple reasons. So when you have a haptic system, there is some kind of finite bandwidth, and you get loop latencies that are probably the biggest cause of oscillation. Also, the phantoms and such, they're actually flexible, and that's also bad. But the solvers definitely make a difference. So in MuJoCo, I've actually hooked that up to a phantom, and yeah, when I make the constraints softer, these things go away. When you make them hard, it's pretty nice. So if you slide the phantom along the virtual surface, you literally hear the friction because the robot vibrates at some kind of frequency that you can hear. Yeah. OK, so this is MuJoCo physics. Now, how do we apply our goal-directed dynamics to it? Remember, again, what was the goal-directed dynamics? We want to solve this optimization problem. Somebody handed us a cost function. We're going to penalize the inverse dynamics, and we'll have these acceleration constraints. So that's our objective. The gradient of that is the Jacobian of MuJoCo's physics that I computed earlier, plus the gradient of our cost function. And the Hessian is also something that we can compute analytically in closed form, and it's all symmetric positive definite. You can do Cholesky factorization. We're all happy. So what we've defined here is non-convex and sadly non-smooth optimization problem. It's non-smooth because the inverse dynamics are piecewise affine, basically. And nevertheless, we're going to happily solve it with a primal dual method. There's a lot of details here that I'm going to spare you, but basically the magic sauce is an analytical line search that's exact, and it's specific to a MuJoCo physics. So basically, it knows where all the constraints are flipping their states and examines them analytically and figures out what to do. And the primal dual method itself, I don't know if you're familiar with primal dual methods, but basically you're solving for the optimization variables and the Lagrange multipliers, and you're estimating them as you go. And the theory tells you that it should converge. In practice, the theory is not entirely true, so you have to be careful. And indeed, most of the high-end commercial optimizers actually use that, and people pay tens of thousands of dollars to use them because it's really hard to get this thing to work. But after a month of tweaking, I got it to work. So here's some results. let me just show you a movie, actually. That's probably easier to understand what's going on. So what you're seeing here is I'm going to drop a humanoid on the floor. And now the cost functions are these. So the energy cost is what I said before. There's a constant joint velocities that says, like, please move slowly. So it's like a virtual damper that the goal-directed dynamics solver has to enforce. And then I'm going to have a target. Basically, I can select a body, and then I have a red target that's going to move around. And my code is going to compute the difference between the selected body and the target, and it will ask the selected body to accelerate in that direction. Right? So that's how my acceleration cost is formed. That's the cost I hand down to my goal-directed dynamics solver. And it's a cost that has a parameter, which is this spatial target, and I get to control it in real time with a joystick mouse. Okay? So here I'm telling it to go up, and it's lifted its butt up, and it does a somersault. Okay? So this is running in real time. It automatically computing what controls it needs, such that when it runs it through its forward dynamics, it would accelerate the selected body in the desired direction. So here it kind of did some kind of thing. Once I disable it, it stays in place because I have this cost saying that I want the velocities to be 0. So it's like a very strong damper, basically. Okay, so here I can kind of get. So see how basically all kinds of contacts are established automatically, and the moment they're established, they are used by the solver. This is an interesting thing. See how it starts to wiggle forward? So when this greedy instantaneous solver interacts with the physics, actually interesting things can emerge. Here I'm just telling it to point its arm in different directions. So it's not exactly a dog that it can sit, but you can see that it's actually quite close to that. Here's the Addams Family hand. Here I'm going to tell the palm to move up, and one of the fingers happened to be on the table. So if I push on that, I can move up. So it did it.
So you showed some early videos that you did with MuJoCo, this stuff, or with the hand, and with Zoran, right? It's the main difference that this is now real time, and the other stuff was.
The other stuff was offline trajectory optimization that was taking 5 minutes to compute. This actually all fast in real time. So now if I put trajectory optimizer on top of that, the whole piece is going to work. So here's conveniently. So if you have a fixed base robot, this becomes something like inverse Knut dynamics of some sort. So here I'm basically telling this arm to go to places. I have one extra cost that says put your fingers in some joint configuration, which basically is a grasp. And now it's grasping, and now I'm telling it to play with it by sort of moving the shoulder around.
Is this trying to go to GPU or regular?
No. This is regular. This is one core of one processor. There's no need for a GPU here. Here it's sliding, but it knows about friction, so it's figuring out how to overcome friction. So basically, whenever contact is established, it's automatically taken into account by the optimizer, and it starts like optimizing through it, basically. So here
you could get it still stuck in kind of a local configuration where it won't kind of do the.
You could. It's surprisingly easy to get it stuck, actually. Plus, you as the human, you're basically the feedback loop, right? So you're going to see that and wiggle it a little bit. And there's trajectory optimizer on top of that. Hopefully, it will figure that too. So here's some timings. This one core. These are microseconds, so very small. So this is about half a millisecond. If you just do the forward dynamics, this is how long it takes per simulation step. If you do this goal-directed dynamics followed by the forward dynamics, it's longer, but still the whole thing takes half a millisecond. I already got on this faster, by the way. I just don't have the numbers. But it really is a dynamical system. So you can forget that there's a computer in it, and you can say that, this is my robot. It just happens to be smart, and it obeys these high-level goals. And now I'm going to control it in that language, and I don't have to talk about torques anymore if I don't have to. Okay, now very quickly, this relates to dynamic programming in a nice and obvious way, actually. Remember what dynamic programming is. So let's write the dynamics in discrete time, position plus velocity, velocity plus force. We're going to have some running cost, which is our control cost, plus some other thing, which is now a long-term cost that we want to optimize in dynamic programming. There's a thing called the Bellman equation, which says the value function is equal to immediate cost plus the minimum over all the controls of the control cost plus the value function of the next state. Right? So this is just standard dynamic programming. Now, we're going to define something that I'm going to call acceleration-based dynamic programming, which relates to what I just did. And it's actually a really nice idea that I haven't seen people use. I'm not sure why. So here's what we're going to do. We're going to define the control signal to be acceleration. And therefore, by definition, the dynamics just became linear and point mass. right? If my control signal is the acceleration, then I have F equals ma. Okay? So I got linear point mass dynamics. Running cost is the same as before. We had control before. Now that we control is acceleration, we have to use inverse dynamics, same running cost. And now the Bellman equation became the same thing as before. And the catch is that now when I solve this minimization problem in the Bellman equation, I have a much more complicated constraint set. Now I'm optimizing over accelerations for which a control exists such that if I run forward dynamics, I'm going to get that acceleration. Right? So usually my constraint set is just a box. This is now some kind of piecewise affine submanifold that has sort of oblique edges. Okay? And the cost becomes more complicated. So basically, I took the complexity that's usually in the nonlinear dynamics, and I dumped it into the control cost. And now if you look at that problem, and if you get this optimal value function at the next stage to be your acceleration cost defined as such, what you see is that the thing we're solving inside the Bellman equation is exactly the thing I defined as goal-directed dynamics. Why is that? It's kind of obvious. So if you remember what optimal value function is, it's a function of the state such that if you act greedily with respect to it, you're guaranteed to get the optimal long-term performance. Right? Because that magic function called the optimal value function, optimal cost to goal function, caches all the knowledge about the future and tells you what to do right now. Okay? These costs that I'm handing down to it, I'm guessing what they are. There's some kind of heuristics. But if I happen to know what is the optimal value function for some control problem, and I hand it down to my goal-directed solver, it will automatically infer the optimal control policy given the optimal value function. Okay, so you can think of this whole thing as the inner step of the Bellman update, basically, except we happen to be exploiting this inverse dynamics and doing it very quickly. And this also tells that these value functions, they're amenable to hacking and guessing. Indeed, if you look at all these game-playing software, that's what they do, right? They have some approximation to the optimal value function, then they do a little bit of optimization on top of it and clean it up. So then this opens up the possibility to do a trajectory optimization on top of it. So in future work, there's a new algorithm. And since AI is back to being fashionable, the new algorithm is going to be called AI LQG. It stands for acceleration-based iterative LQG. So basically, it's the LQG algorithm applied to this acceleration-based dynamic. We can obviously design more interesting costs that make these characters do fancier things. I've been focusing on the optimizer, so I haven't had time for cute demos. Designing cost functions that are efficiently evaluated and differentiated is key. Like once you have a library of those, anyone can start playing with this and see what happens. If you don't have that library, people have to write code, and they're not going to do it well, so it's going to be a mess. And then once my hardworking students get around to developing the state estimators they've been developing for a while, we can actually run it on real robots in the lab because it's kind of ready to go. I mean, we have joysticks. We can give it spatial targets. We can see what these things can do. So that's it. Thank you. Any more questions?
Any limitations or any on the representation? Like, how do you represent in your simulator, like the parts or so? And
well, that's a simulator side, right? So
which is important.
Which is important, and which I already have working. So yeah, you write an XML file that specifies the model, or you can load the URDF. You have meshes and all kinds of softness parameters for contacts and such, and just simulate stuff. So this plugs in very nicely in the simulator. I mean, the limitation is, again, you're solving a non-convex, non-smooth problem. There's no way you're always going to solve it exactly. So you're going to solve it as much as you can, and then you're going to take whatever you have and run it through the forward dynamics, basically. Yeah.
You mentioned that you use kind of whatever contacts exist to kind of push in whatever direction you want.
Yeah.
But it doesn't sound like you're also generating new contacts that might be useful.
Correct. That would require forward planning. So that's where trajectory optimizer will come in. So once you put a trajectory optimizer on top of it, it will have to reason about the geometry of the contacts, but it will not have to reason about the physics anymore because it can think of being an acceleration space in some sense. No, I mean, not entirely, but roughly. But yes, you're right. It's right now, this is relying on contacts just emerging from the complicated physics. Interesting thing here is that the more contacts you have, the better this works. Right? So one thing I'm thinking of doing is, I suppose I have put an object in my hand, and I tell you spin the object. There are enough contacts to actually do quite a lot. Question is, would it figure out to reset the fingers? So maybe there's some simple cause that says spin the object and try to reset your fingers at the same time, and it's possible that something would emerge, just like this little humanoid started crawling on the floor, which is basically an emergent property of the physics, and this greedy thing. But yeah, that's a great question.
Can we do estimation using this? Basically say that represents the sensor value.
Of course, yeah. So this cost could be a likelihood cost. Yeah.
So like we still need to do calibration so that the sensor.
You would need to figure out the generative model of the sensors that would tell you how to design the data likelihood cost. Yeah. So this solver could be used to solve part of the estimation problem. Here I assume that position and velocity are fixed and they're known, and I'm only optimizing over accelerations. In estimation, you're actually varying all of them, so it is a bigger problem, but this could be the sort of part of it. Yes.
So how are you planning to get the value functions? Are you just going to roll out trajectory optimizer and get them?
No, literally do put LQG on top of this with linear dynamics and horrendously complicated control cost.
Okay, so that is going to tell you the sequence of positions that you want your goal dynamic.
No, LQG gives you a local quadratic approximation to the value function that you propagate backward to time. You could also try to use that in a reinforcement learning setting where you train some neural network with a policy gradient where the control signals are these costs instead of the low-level commands. Actually, the thing that I showed you that we did with Igor with the walking software and all, that was kind of like this. So we built a neural network that actually gives you desired accelerations rather than commands. And then we did a little bit of physics cleanup, which wasn't as efficient as this, but kind of worked. So it looks like a neural network is actually happier if it has to learn acceleration signals rather than controls, because that space is somehow simpler.
So you're optimizing over these softened constraints, but are they projected back onto the actual hard constraints? Or, for example, in that Django video, is the tower slightly epsilon shorter than it should be?
So, so the physics that I showed you is the one that I'm optimizing through with the orange humanoid and the hand. It could be made harder, so it will make the systems slightly harder to solve. So if you look here, when the constraints become harder, these J's are going to get bigger, right? But if you are factorizing this thing carefully, it's not actually a big deal. So I think you can make them pretty hard, and it doesn't. The contact hardness gets tricky when you're optimizing over time. But here you know which contacts are on and which contacts are off. So within that space, making them harder doesn't seem to make it. Apart from the numerical conditioning here. But again, with double precision, you can go very high. Probably higher than the Django thing was.
I guess the high-level idea is it needs to be just hard enough to where locally the dynamics are realistic and the physics possible.
Yeah, and again, that's not a problem. So the thing that I showed you with the orange humanoid is a relatively soft dynamics on the scale of MuJoCo, but it looks very realistic, and we can make it a lot harder than that. Yeah.
I know you don't care about this anymore, but the acceleration-based kind of control, is there any connection to biology or any idea how?
So if you look at what biology people have been doing, it's a very interesting argument. So this fight has been going on for over a century. The fight is over what does the brain control? Now you might think that's a really dumb question. Obviously it controls muscles. What else is it going to control? But the implicit assumption has always been that there is this hierarchy internally. The high levels of the brain, which people call the brain, control something else. And there's some lower level system that takes that and maps it to muscle commands. And the biggest fights in motor control have been exactly about that. So there's something called the equilibrium point hypothesis due to Feldman and Campri. I don't know if you've heard of it, but it's basically servo control. It says that the brain hands down position commands and the spinal cord acts like a computational position servo, basically. There was the whole population vector thing due to Georgopoulos and colleagues, which was really hot for a while. The idea there was the motor cortex controls the direction of movement in a Cartesian space, much like a Khatib-like operational space thing, and then something underneath resolves it. More recently, the latest thing based on neurophysiology is from Christian Chenot and Mark Churchwand, looking at this, basically showing the motor cortex is some kind of big dynamical system that has surprisingly simple dynamics in a million-dimensional neuron space. It's kind of a rotational thing. And so they show that you can think of executing a movement as initializing that dynamical system in the right state and just let it go. Its intrinsic dynamics supposedly give rise to natural movements. And in that case, it's not even clear what you're controlling. But a lot of the fights on the biological side have been about that. There's another thing called synergies. The idea has Santel and John Sechting and company have been doing that, and a lot of the hand manipulation people have picked up on that. So the idea is that you have a few high-level control knobs that control the overall shape of your hand, and then that manages spatial complexity of your hand, and then something upstream tweaks the knobs. So all of these things are really special cases of this very general notion that we're going to have an instantaneous optimizer. You talk to it in whatever cost functions you want, and it's going to optimize them for you. So this kind of subsumes all these ideas, and I'm trying to actually not commit to any one of them, but write a general purpose solver that enables everyone to test their own favorite theory. Good question. Yes.
In the video with the arm and the hand on it, and it was sort of using friction to slide along the...
It was overcoming friction. So I was telling it to slide, and it was pushing enough so that it overcomes friction and slides. But it's, at the same time, it has a cost saying keep your fingers closed. So these two are fighting. In general, my approach is to, like, if you have multiple objectives, is to mix them up with different weights, and you have to tune those weights. Another approach is to do hierarchical optimization, where, like, you have a hierarchy of costs. You first optimize the first one and see what's the best I can achieve on that cost. And now fix that to a level set where that cost has that value, and then go optimize the second one until you run out of degrees of freedom. People with the QPs have been doing that. But in this much harder optimization setting, it's not at all clear that you can pull that off. So I'm stuck with mixed costs with weights that somebody has to tune, and yeah, they can fight. It doesn't seem to be hard to tune them. I probably spent like 5 minutes tuning them to get those videos. And the round numbers like 10,000, 5,000.
Right, let's thank Emma once again.